Ever wonder how your engine knows exactly how much fuel to mix with air every time you stomp on the gas? Maybe some kind of high-octane voodoo? But really, it's math. Glorious, greasy math. Now let's talk about one of the brains behind it all. Speed density. Speed density is a method your engine's computer, whether you call it an ECM, ECU, or just that little box of sorcery, uses to estimate how much air is rushing into the cylinders during the induction stroke. That estimate is the starting point. Once the ECU has a good guess of how much air just came in, it uses that to calculate how much fuel to inject. Why? To hit the right air-fuel ratio, or AFR. The engine already has targets for how rich or lean to run. Those AFR values are mapped out ahead of time for different conditions. Cruising, idling, flooring it, it's all in the tables. So once the ECU knows the air and the target AFR, it calculates the fuel needed and opens the injectors for just the right amount of time. That's called injector pulse width, and it's how long the fuel injectors stay open. Oh, and the ignition timing, load, RPM, airflow, it's all connected. Speed density doesn't directly spark it up, but it gives the ECU what it needs to look up the right amount of ignition advance from a spark timing table. All of this, the air estimates, the fuel delivery, the timing, it's a coordinated dance between the sensors, the tables, and logic. And speed density is right at the center of it. Now don't worry, we're not throwing you headfirst into chemistry class. We'll ease into the smart stuff a little at a time, just like a good warm-up lap. Now the key here is predicting how much air the engine takes in during something called the induction stroke. That's when the piston dives down and sucks air into the cylinder like a smoothie through a straw. Pull this off, the computer leans on a few trusty sensors. One for RPM, revolutions per minute, which is basically how fast the engine's spinning. A MAP sensor, short for manifold absolute pressure, which reads how much pressure is in the intake manifold. An IAT sensor, which grabs the intake air temperature. And an ECT sensor, which checks the temperature of the engine coolant. This gives a good clue about the overall engine temperature. Together, these sensors try to answer one big question. How much air just went into the cylinder? And here's where the ideal gas law sneaks in. The whole speed density approach is based on a classic science formula called the ideal gas law. But let's not panic, it's just a way to estimate how many air molecules are in the cylinder. That's what N is. Think of it like counting how many breaths the engine just took in. So to use this formula, we'd need to know the pressure in the cylinder, the volume of the cylinder, the temperature of the air inside, and a constant R that just comes along for the ride. Pressure P times volume V equals the number of gas particles N times a constant R times temperature T. When rearranged, it lets the ECU estimate N, or how many moles of air molecules are in the cylinder. But reality isn't so tidy. See, the MAP sensor doesn't measure the pressure inside the cylinder after the intake valve slams shut. It just measures what's going on in the intake manifold. And that temp reading, it's not actual temperature of the air-fuel mix in the cylinder either. The engine guesses it, blending readings from the IAT for incoming air and the ECT for engine temp, and the ECU has to estimate the actual air temp in the cylinder based on those two numbers, and maybe even a little bit of wizardry. That guesswork is what we call density correction, and it affects how dense the air is, and that changes how much oxygen we have to work with. This guesswork is kind of the Achilles heel of this whole system. And to make up for all of that uncertainty, engineers use a trick called volumetric efficiency. Think of VE as a correction factor. It's the ratio of the actual amount of air entering the engine's cylinders compared to the maximum theoretical amount of air that could enter the engine cylinders. The VE ratio tells us how efficiently the engine cylinders fill with air during intake. A VE of 100% means the engine is taking in all the air it can, but most engines aren't that lucky. They're more like 70 to 90% efficient most of the time, unless you've got something spicy like a turbocharged Honda. Then you might even sneak past 100% with a little help from forced induction. So VE is the primary factor in speed density systems. Speed density is typically applied where there isn't a mass airflow sensor present or integrated in the ECU. VE uses manifold pressure instead of cylinder pressure for our P pressure term. You can see the VE tables along with the sensor values are really all the ECU has to make those decisions. Speed density tunes use those VE tables, which look like big grids, to help the engine guess how much air it's really intaking at different RPMs and loads. Adjusting those tables is really the bread and butter of tuning this type of system. The more accurate they are, the better your engine runs. And now for the fun part, why this system rocks and where it stumbles. Strengths: no airflow restriction like a mass airflow sensor. Air just breezes right in. It reacts fast. The map sensor picks up changes almost instantly. It gives you loads of control compared to old school carburetors. And look, these sensors are tough, reliable, and kind of cheap. Weaknesses? Remember that temperature guessing game? Well, the density correction can be a beast. Seasonal changes, altitude, turbos, they all throw wrenches into the works. Got a wild camshaft with crazy overlap? Well, expect weird vacuum signals, especially at idle. VE tables are time-consuming to dial in, no doubt. And if you bolt on new parts, yep, you're back to the tuning laptop. And yes, there's math. Lots of it. So much that older ECUs had to take shortcuts just to keep up. So how do tuners keep their sanity? Well, VE tables should look smooth with no sudden spikes. The more vacuum usually means less VE, and peak VE usually lives around the engine's torque peak. Also, don't forget those sneaky other tables in your ECU, things like temperature correction tables and injector battery offset tables. They also shape how fuel gets delivered. They matter a lot. So let's recap. Speed density system, the ECU estimates airflow using MAP, RPM, IAT, ECT, and engine displacement. It then looks up a target AFR based on current RPM and engine load. And with those two pieces, the ECU calculates how much fuel is needed to hit that AFR. Finally, it sets the injector pulse width accordingly. So until next time, keep learning, keep flowing, boost when you need to, and we'll see you in the next video.